recording whenever you want. I'll set it. So the damped driven oscillator, let's say mass on a spring. Then has this picture hanging down from the ceiling on a spring. Extended some length U from the equilibrium position at U equals 0. It has now possibly some object maybe attached at this end. And we'll call this a dashpot damper. Here's going to make kind of a shape like this in 2 dimensions. And the net force then is mass times acceleration by Newton's law. And that has to equal the damping force from this damper, so it's minus C du dt. Added, we say forces add, as an experimental observation, which holds true when you're not near the speed of light, plus the spring force, which is minus Ku. And again, this is minus, so it's a restoring force. This is minus, so it opposes the direction of velocity. And tries to slow it down. Right? And then there's a driving force. And now you rewrite that equation, and we come up with this for the damped driven oscillator. Damped driven mass on a spring has this equation. When you rearrange that, we'll divide it by, let's see, yeah, let's write it that way. M d squared u dt squared plus C du dt plus Ku equals some driving force. Let's put the OT on there just to be suggestive that it generally depends on time. And there it is. There's the big equation for today. Call that number 1. Look what it is. It's constant coefficients, constant mass, constant damping coefficient, constant Hooke's law coefficient equals a function of t only. It's precisely the equation I wrote at the beginning here. And so we can try and solve this, right? Because we have our techniques. The interesting case is when F drive is an oscillating force. Sinusoidal in nature. So I'm going to break this up into 4 cases that can occur with this object. The first one is the undamped, undriven case that I already wrote up there. If it's undamped, in other words, no dashpot damper down here, and it's undriven, no F drive equals 0. Then the equation reduces to this: m d squared u dt squared plus Ku equals 0. And how do we solve that one? It's very easy, right? Constant coefficients. You write this with the characteristic equation. Mr squared plus K equals 0. You get R squared, R equals plus or minus square root K over M times I for the solutions of the characteristic equation. And what does that tell you the solutions are? Remember these things, you have them all tabulated. You go to that table, you say, oh, I know what the solutions are. The solutions are u equals an arbitrary constant times cosine square root k over m t. Remember, when it's pure imaginary, you just get a cosine and sine for the two solutions. Plus c2 sine square root k over m t. That's it. General solution in the undamped, undriven case. Any questions on that so far? It's a good stopping point to ask. Okay, so this is the general equation we're looking at for a possibly damped, possibly driven mass on a spring. Spring is always there. Here's the first case, no damping, no driving. We get the solution. Beautiful. All we have to do is apply initial conditions. This shows you immediately that if you give me the initial position and the initial velocity, what do you get? The existence uniqueness theorem says we get a unique solution. So if you can tell me where it starts and what velocity it starts with, I know it's motion for all time and eternity, right? So that's what that says. Now that's a theoretical result, assuming there's no damping. In real life, the spring gradually winds down, but if it wasn't experiencing any damping, the thing would just oscillate like this forever. And now comes the easy part of today, hopefully, trigonometry. You can get some insight into what that looks like by rearranging it. So I'll say, if you apply two initial conditions, that will determine C1 and C2. Maybe I should write that down. Initial conditions, or the initial values on them. Initial values for position and velocity determine C1 and C2 uniquely, because when you plug in those initial values, they give you a system of two linear equations and two unknowns, and from linear algebra, you can always solve it. And this will give you a unique solution, because cosine and sine are independent functions. It leads to independent linear equations always. All right. Some of that is over your head if you didn't take linear algebra. It's okay. It just always determines a unique solution. All right. Now, what does that solution look like, though, for physicists and those kind of people? It's real important to understand what that behavior is. Anybody seen this before in your physics class, maybe? Oh, okay. This helps me gauge how fast to go. So if you want me to go faster, speak up. All right. What you do now is, by trigonometry, you do this. You let A denote the square root of C1 squared plus C2 squared. Whatever those constants come out to be because of initial conditions, you're going to let A be that number. And you're going to let a variable phi equal a tan 2. Remember we mentioned the a tan 2 function before of C1 over C2. C1. Maybe I better just do arctangent. But let's do it this way. Tangent phi equals C1 over C2. Or you put it in the correct quadrant. So you use the a tan 2 function to get it out. This is better. This is complicated. Well, C1, C2, C1. is in quadrant 1, then this is just arc, or 4, this is arctangent. If it's in quadrant 2 or 3, it's arctangent plus pi, is what you can do. All right, so we make those definitions. All we're doing is a change of variables from C1 and C2 to A and phi, right? And the initial conditions will now determine A and phi instead of C1 and C2. But now look what happens. Let's call this equation 2. Equation 2 is the following. U equals square root C1 squared plus C2 squared times C1 over square root C1 squared plus C2 squared. This is all easy tricks in algebra, but it goes fast enough to be confusing, so stop me as I go too fast. Cosine square root K over M P plus C2 over square root C1 squared plus C2 squared sine square root K over MT. All right. All I did was I divided in here by the square root, multiplied outside by the square root to cancel. It's just algebra at this point. But now this is U equals A, because I defined this to be A. And what's C1 over square root C1 squared plus C2 squared? This is actually the sine of phi. The idea is that here's phi, and this is C1 and C2, and this is square root C1 squared plus C2 squared in a triangle, right? So the tangent is this over this. Then the cosine is C2 over this, and the sine is C1 over this. Aha, there it is. So a triangle is very helpful, right? And so this is sine phi times cosine square root K over MT plus cosine phi times sine square root K over MT. I hate to bore you with trigonometry here, but it really does. It really does provide an important insight into these. I'm going to leave equation 1 up here. I want to refer to it again. So that's the motion. And now, wait a minute. Sine, cosine plus cosine, sine. Here's the trig. What is that? Somebody remembers trig, right? The sum of angles formula. Sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. That's why we make you learn all this stuff. So when you get classes like this, you can use it. So equivalently, this is U equals A times sine of the sum of the angles. Square root K over MT plus phi by trigonometry. The sum of angles formula for sine. Nice thing is these days, if you're ever stuck at home working on this stuff, you can't remember that formula. It takes about 5 seconds to bring it up online, a whole sheet of trig formulas. So really nice. You guys are going to be so much smarter. I am so much better off than my professors because I can look up anything I want. It really helps my research. You're going to be even better off because you got more earlier. I didn't get started on this stuff till I was out of graduate school. So with internet stuff. All right. So this is also the motion, right? This is absolutely the same equation that we wrote here, right? It's the same equation. I just rewrote instead of C1 and C2, A and phi. And so it's another way of writing the same thing. It's the same motion. What is this motion? Here's t time. Here's u, the displacement downward from vertical, right? We're saying downward is positive. Go either way. I think downward is easier. And this is a sine wave with a phase shift of minus phi over square root K over M, if you remember the phase shift, and an amplitude of A. So it goes up and down between plus and minus A. And there's some sort of phase shift. There's the guidelines, if you like, from trigonometry. And it goes like this. And it has a period, so that it repeats itself maybe here. 2 pi over square root k over m is the period, right? Remember from trigonometry. And the phase shift is whatever, subtract or minus phi over square root k over m. So there's a phase shift here. But that's what the motion is. It's just this sinusoidal motion that we call simple harmonic motion. Harmonic motion is one that repeats over and over with a period. Simple harmonic motion, they usually mean sinusoidal harmonic motion. So it's a simple harmonic motion. Physicists will say, when it's a sine wave. Which includes, if you put cosine here, that's the same thing shifted over too, right? Any questions now? All right. So when you put a mass on a spring, it just does that. Let's see if we can do an example here. Actually, maybe I should bring up my picture now. Here's my little gifts I put together some time ago. Yeah, so it does a sinusoidal type motion there in time. Plotting this thing on the side. Now, what's going to happen if we attach a damper to it that opposes velocity, the directional velocity, with resistance proportional to velocity? Here's what you get. There's my dash pot damper down here. You know, I said that friction through the air is proportional to velocity squared. That's true for any macroscopic object. If you get things that are small enough and moving slowly enough through air or a fluid, sometimes they count air as a fluid for aerodynamic purposes. And it moves real slowly, you can actually have resistance proportional to velocity. So here I put a damper, and if you have something sticking down in here, it goes real slowly through the water, so there's no turbulence. You can actually create a force proportional to velocity. But it's usually not something you experience. So we draw it this way anyway. So here's the motion you get. It's going to actually, instead of doing a sinusoidal motion, it tries to be sinusoidal, but it's also damped out. It gradually goes out. And we'll see the equation that represents that one soon. Okay. So let's put an example up here. Here's my first example. Suppose in the meters kilogram second system, the MKS system, we take a 1 kilogram mass with a Hooke's law constant of K equals 4, which is newtons per meter if you figure it out from the equations. It can be written in other ways too. And you pull it 8 centimeters below its hanging equilibrium. I pull it, so U is not 8, but 0.08, since you're doing things in meters, right? So you have to convert this. With an initial velocity upward at 12 centimeters per second, so 0.12 meters per second. Is this initial velocity, initial position, initial velocity? I can find the motion for all time, right? For the theoretical motion for all time. So the motion of the mass for t greater than or equal to 0 is desired. Here's what I write down, and maybe I better write the problem on the board here. Example, suppose the mass is 1, the Hooke's law constant K, I'll move the camera in just a second, is 4, and There's the other things, they're not in there. This is damp pen driven motion. And then your initial position, since you pulled it down 8 centimeters and down is positive, this is 0.08. I'm going to move the camera there. We have these, and then the initial velocity is upward. That makes it negative because it's in the opposite direction of u positive at 12 centimeters per second. So u prime of 0 equals minus 0.12. There we go. So here's how you do an application. And like I said, even though this seems like a silly idealized object, what happens in real practice is if you have a girder and a bridge, for instance, to a first approximation, when you compress it, it behaves like a mass on a spring, and you can send vibrations through it and so forth. But what you can do actually, as an engineer, is take all these interacting girders and think of them as systems of differential equations with the interacting masses on springs. And I have a neat video of that for you, actually, sometime. So here is this one. And we put it into equation 2. This in equation 2 gives solution for the mass on the spring. Well, let's see, we've got 1 times d squared u dt squared plus 4 times u equals nothing. That's equation 2 with, not 2, 1, sorry. Since C and F drive are 0, that's what we get. This is easy to solve, right? The characteristic equation implied by this is r squared plus 4 equals 0. Tells you that r equals plus or minus 2i. If you're imaginary, tells you that solutions are cosine and sine. C1 times cosine 2t plus C2 sine 2t is the general solution. I can, from the initial values, determine what C1 and C2 are. Oops, I put y as CU. Apply u of 0 equals 0.8, 0.08. Says that 0.08 equals C1 times cosine 0 is 1, plus C2 times sine of 0 is 0. Right? Then I also need to plug in the derivative. I should have erased that. The derivative, u prime, looks like 2c1 minus 2c1, applying the chain rule, sine 2t, plus 2c2 cosine 2t. I'm taking the derivative of this one. And then I put u prime of 0 equals minus 0.12. So I put minus 0.12 over here and put in 0 for t. And this gives me prime of 0 equals minus 0.12. Says that minus 0.12 is minus 2 times 0, because sine is 0, plus, that is 0, plus 2c2 times cosine of 0 is 1. And now I have it. This one says quite easily that C1 is 0.08. This one says, in this case, quite easily that C2 is minus 0.06. Evidently, the motion is u is equal to 0.08 cosine. And now I need, let's see, cosine 2t minus 0.06 sine 2t. There it is. That's the solution to this mass on the spring problem. More suggestively, if you take A, the amplitude, equal to the root sum square of those coefficients, 0.08 squared plus minus 0.06 squared square root. you get 0.0, you get 0.1. And the angle, if you take tangent phi equal C1 over C2 is minus 0.06 over 0.08 is minus 3/4. And then you say, well, I want let's see. I want the y coordinate C1 to be positive and the x coordinate to be negative. And so I'm over in quadrant 2, thinking this is y and this is x for just for purposes of phi. So put phi over quadrant 2 so that you get minus 0.06, 0.08. Here's a is the length. Then it's not arctangent, but tangent, but arctangent plus pi. So we'll say phi is therefore arctangent minus 3/4 plus pi. And I wrote it up here somewhere. Thing. It's about 2.0 radians, it looks like. Wait a minute. No, that's not right. I didn't write it up. Oh, the next one. Here it is. Let's see. It's about 2.2. There it is. Rounding to 2 digits since the other ones were presumably rounded to 2 digits. And now we have, therefore, in the more suggestive format, u is equal to 0.10 cosine 2t of sine of twice t plus 2.2, like that. It's an a sine square root k over m t plus phi. That's that later format. And if you really think about it, you don't have to go through all these intermediate calculations. I gave you the formula. You could just immediately put this in once I give you the numbers at the beginning. But you just compute a and phi and write this down if you want. But I like to solve the differential equations, so I feel like I understood what I'm doing. Questions on that one? All right, so that's the first case. Now get rid of it. Let's do the second case. Oh, yeah, all right. It's damped undriven. So you put in the dashpot damper, but you don't apply an external driving force. And that looks like this. D squared U dt squared. That's the one I was showing you there with the damper on it. plus C du dt plus Ku equals no driving force. What do I do with this one? Oh, it's constant coefficients homogeneous, the easiest case, right? So I immediately write mr squared plus cr plus k equals 0. It's the same thing we did before. Ar squared plus br plus c equals 0. How do we solve it? We write the characteristic equation and we can use the quadratic formula. R1 and R2, the solutions are just minus b, or in this case minus c, plus or minus square root b squared minus 4ac becomes c squared minus 4mk. All over 2a is now m. So it's the same thing as before, just with different letters. You don't have to memorize these letters. You want to switch it to A, B, and C. This is just convenient for applied problems. And now, what do I do with those? Remember, in the constant coefficients case, this breaks up into 3 different cases. So our case of damped undriven motion breaks into 3 subcases. One is if R1 is not equal to R2. And what does the quadratic formula tell you you're going to get R1 not equal to R2 real numbers? Remember? Algebra, right? C squared minus 4mk is positive. You get 1 for the plus and 1 for the minus. But C squared minus 4mk positive makes you a positive square root here. And you get 2 real distinct solutions. Then what happens if these are not equal real numbers? The solution is u equals C1 cosine not cosine, I'm sorry, C1 e to the R1 t plus C2 e to the R2 t. There's the solution when you have, remember, 2 real not equal solutions to the quadratic formula. Now the second case we had was suppose that R1 is equal to R2 or real. That happens when the square root's equal to 0, right? You get plus and minus give you the same solution. So R1 is equal to R2. Now, what we said before is in that case, you get C1 e to the R1t, and R2 equals R1, so an independent solution is T e to the R1t. There's your solution. Finally, the third case that it can occur with the quadratic formula is you can get complex conjugates. If this thing under the square root is negative, then you'll get imaginary numbers in here, well, complex numbers. R1 and R2 will be complex conjugates since these initial numbers CM and K are all real. So the complex conjugates alpha plus or minus phi beta, where alpha is this part and beta is this part, the part that has the I in it. This will be beta I guess I should say. But you'll get 2 complex conjugates. You won't get other complex cases because you started with real numbers here. So this is if the thing under the square root is negative. Now, in this case, you remember when you have complex conjugates, the general solution is u equals C is equal to C1 e to the alpha t cosine beta t plus C2 e to the alpha t sine beta t. You thought you were all done with that section. That's all right. It'll be good review for the test, right? Need to do this on the test. This stuff will not be on the test, the applications. However, these equations we did before will, right? So what we've got here is this table, analogous to the table we had for solving constant coefficients. Just, it's a real application now. so what happens in these three cases? Well, regardless of the initial conditions, what happens is this. If you look at alpha, it's minus c over 2m. Alpha is always negative, right? Minus c. C is m, c, and k are positive because they're physical positive constants. Right? K is the spring constant, it's positive, so it's damping. C is a damping coefficient, so it opposes velocity. M is mass, so it's positive. Since they're all positive, minus c over 2m is negative, and what you get is alpha is always negative. And this is damped motion, which is what you'd expect from a damper, right? So sometimes it's having intuition though. But what you now get is these three cases. These are all decaying exponentials because similarly here, you can figure the same. And with these all positive, R1 and R2 always have negative, are negative real numbers or have negative real part of their complex conjugates. So if you start it here in the TU plane with some initial position, U of 0, axis. So it starts here, and maybe you start it with a little downward velocity, so it has negative slope here. It might go like that, right? It damps out exponentially. It doesn't ever touch the axis, but it just gets lower and lower. So this will be case 1. And we call this case 1 overdamping. But what happens is one of these is more negative than the other. Whichever one is the least negative dominates, right? Like if R1 is -1 and R2 is -2, which one dominates? This one with R1 equals -1 because it decays slower, right? The more negative R is, the faster it decays. So this one decays out much faster than this one. And whichever R is less negative drives the motion. Eventually, it just looks like a single exponential because the other one's so small, relatively small, I should say. They're both damping out quickly because they're exponential decay, right? Now, in the second one, we have almost the same thing. This one's multiplied by t, but you remember from calculus, what does t e to the R1t go for if R is negative, R1 is negative? This one grows and this one shrinks to 0. Which one dominates? For exponential dominates, we used to do these problems like limit. T goes to infinity of t over e to the minus t or something like that, where you had over t over e to the t. Exponentials grow much faster than any polynomial of any power. And so this was 0. And same thing here. If you think of this as 1 over e to the positive exponent t, it looks like this. The quotient is driven to 0. So this thing is still going to go to 0. T makes it larger, but this makes it smaller very fast. The exponential decays much faster than t grows. And so in the second case, so the white one is case 1. In the second case, maybe you started off with the same, you started off like this, and it decays a little slower. No, what do I say? I'm sorry. It decays a little faster. All right. It decays a little faster down to 0, like that. Because what drives this is the smaller of R1 and R1, and you can show with the initial conditions. If you started with the same initial condition, the same K and M, this one damps out faster is what happens. And then this case here, what does this look like? Here's a trick. We use our old trick from the undamped undriven motion. We write this as e to the alpha t times c1 cosine beta t plus c2 sine beta t in this third case. And what's that look like now if I factor out the e to the alpha t there? For this one can be written as a single sine wave. So the last case here only, you can read it and write it as e to the alpha t times a sine beta t plus phi a single sine wave times a decaying exponential. Remember, alpha is negative. I told you it's a lot of information fast. That's why you have to stop me once in a while. So it's actually a sine wave times a decaying exponential. What you have is this kind of motion. Here's the u equals e to the minus alpha t, the decaying exponential, right? We know what minus that looks like. It's just turned upside down. Here's u equals minus u. Let's call this u equals a. And here's u equals minus a e to the minus e to the alpha t. Two decaying exponentials, plus a e to the alpha t minus a e to the minus alpha t. That's multiplied, and I should have put the a in here. That's my mistake. This part. Oh, no, that's okay. Yeah, so I was rewriting this. That's okay. But now a sine is a sine wave. Sine of beta t plus phi is a sine wave that multiplies the decaying exponential that I wrote up here, plus and minus. So this oscillates between plus and minus 1. It forces you up and down between the decaying exponential a e to the alpha t and minus that number, right? Since you're multiplying by a number between plus and minus 1. But what you get in this case is something that goes like this. That's what we saw in that gap-driven mass in the spring before. So this is case 3 in blue. This is case 2 in yellow. And case 1 in white. And as I said, the first case, maybe I should write it over here because I'm cluttering. In damped undriven motion, what you get in case 1, overdamping. You can imagine this is kind of like your shock absorbers in your car. Your car wants to bounce up and down, right? And if you damp them, you can damp them too much and you go over a bump and and then it kind of gradually settles down to the middle, you know. That's this one right here, the white one. Returns slowly to equilibrium here at u equals 0. If you actually damp them a little less, then when you go over the bump, it gradually settles you down to the middle. That's this one. That's called critical damping. It returns you fastest to the equilibrium position, faster than the other two cases. You can show. Or you can underdamp it. If you hardly give it any shock absorbers at all, it just, go like that for a long time after you go over the bump, and it doesn't settle down very fast either. So you have to damp it just the right amount to make it return to equilibrium as quickly as possible is critical damping. That's when c squared minus 4mk equals 0. So this one's under damping then if you don't put a large enough damping coefficient. Those are the three names in the three cases, and what you see is the case 2, the yellow one, gets close to the t-axis fastest of the three. Now, what you can do actually, if you give these things a push, you can make this drawing a little different. You can push it hard enough that these two cases that I showed you settling down go through once, but then they'll just return after that. So you make them cross them once by pushing them fast enough towards the equilibrium position. All right. But once they've gone through once, they won't return again. Where this one oscillates forever. The one's oscillatory and the others can cross it most once the t-axis. And that is the second case. I have a picture up here I can show you. This is what's great about MATLAB. See, I didn't have that either when I was a student. Here's a computer graphics to make it much clearer, hopefully. This is for, again, I'm sorry about these bad characters. It's the font. It's not translating right. I'm going to see if I can get the notes fixed. But it's the one we just did, as I recall. Let's see. U double prime plus Cu, where C is the damping coefficient, U prime plus 4u equals 0. So it's u double prime plus a constant times u plus 4u equals 0. Spring constant 4, mass 1. And then C, we're going to let be different numbers. If the damping coefficient is 2, not very much damping, this is the solution of the equation. You can see it oscillating. C equals 4, critically damped, then it returns faster. And so with these same initial conditions, initial position 1, initial velocity 0, I just let it go, right? From 1 unit out. Over damping, if I put C equals 5, then it goes like this and settles down slowly. So there's the actual computer picture better than I can. This is time and this is this displacement of equilibrium. Okay. I got no comments today from the peanut gallery, so I know shouldn't. If you have any questions, let's see. Now we want to move on to the third case, undamped driven motion. Suppose now there's a driving force, but no damping. This one, you take that first equation and you put C equals 0. Right, the damping coefficient, because there's no damper. And now you've got md squared u dt squared, mass times acceleration, plus no damping, plus k times u for the spring force, equals the applied force. And let's say that the applied force is some A0 sine omega 0 t plus d0. And suppose this is the interesting case. You can put whatever force you want here. Right? But suppose the force is sinusoidal, right? A sine wave. And you might think, when does this ever happen? It turns out, though, there's an exact analogy to this with the numbers meaning different things in electronics engineering. And then this is your voltage. So if you have an alternating voltage applied, then this is exactly what you're going to get in the circuit. So it actually has important applications. Or if you've got another beam, in this case, attached to your first beam, it might introduce a sinusoidal vibration, right? So this actually can happen in practice. It's the important case. What happens here? Well, you remember how to solve these non-homogeneous problems? You first solve the associated homogeneous problem, UH, MUH double prime. Plus K to H equals 0. And you wind up with R1 and R2, like we did before, R plus or minus square root K over MI. Oh, that's just the homogeneous solution is just the undamped undriven one that we did before. So now we have a homogeneous solution, which is just the first case. It's an arbitrary constant times cosine square root K over M T plus another arbitrary constant times sine square root K over M T. All right? Easy. You memorize it all, right? I'm sure it's hard right now. It's always hard right now. So I did this equation here. This time I put C equals 0 and I got what's left. This case 3. Last time we put F drive equals 0, got all this equals 0. So we're all working out of equation 1 here. Sometimes we let damping be 0, sometimes we let the driving be 0. In the first case, we let both of these be 0 and just got that equation. All right. Now, what's the particular solution by undetermined coefficients? This actually breaks up into 2 different cases. Better watch my time here, huh? One, if omega, we'll call omega the natural frequency of the oscillator. We'll just make this definition, so I'll put DEF here. That's the natural angular frequency, I should call it, not the frequency, angular frequency. Means radians per second rather than cycles per second. Right, it's what occurs in the homogeneous solution. And what can happen here is if this is not equal to, so this is, we'll call this the, or let's say let that be the case. If omega is not equal to omega naught, frequency that you're driving the object with, right? So the spring wants to naturally go with that frequency that we got in the first case, right? It's going to be a sine wave that has some frequency over the period. And then we're going to push it with a different frequency sine wave. What's going to happen? By undetermined coefficients, remember, when these two aren't equal, what you always get is a particular solution, U particular, which is a constant times cosine plus a constant times gamma 0 delta 0, a constant times sine. So that will be the solution. Moreover, by the first comment we do with trigonometry, this could be rewritten as another sine wave as A0 cosine omega 0 t plus phi 0, using the same prescriptions we did there before, where A0 is the root sum square of those. So it can be written either way. You can write it this way, that's out of the table. Or if you use our trig trick, we can rewrite it as a sine. Sorry about that, sine. You can write it that way. And then tangent phi 0 is gamma 0 over delta 0. And so you can rewrite it as a single sine wave. And what you see is the particular solution contributes a sine wave, and the homogeneous solution contributes a sine wave, and UH is their sum, right? I'm sorry, the solution is their sum, U homogeneous plus U particular by our previous theory. That is, for the undamped but driven motion, you get U equals some number A cosine square root K over M P plus phi plus A naught. I guess I wrote sine before, sorry, sine plus A naught sine omega naught T plus phi naught, where this is the particular solution and this is the homogeneous solution. These are specific numbers because they come, omega 0 is given, that's the given driving frequency. A0 and phi 0 are the specific constants determined by undetermined coefficients. So these are specific numbers, they're not arbitrary. They're determined by an undetermined coefficients method. You plug it into the differential equation and see what they are. So by undetermined coefficients, those are specific numbers. But A and phi and K and M are given. A and phi are arbitrary constants. They're determined by the initial condition. So you put in the initial conditions, it just determines these two. But everything else is set. All right, so now what do you get out of this? Oh, I forgot something. It's A times write it down right here. U homogeneous is not this, right? Oh yeah, I'm sorry, this way, yeah. Okay, so this is good, and what we get here is a sine wave plus a sine wave, sum of sine waves is the solution in this case. And so you have like a big sine wave from one of them, maybe. And then a little sine wave from the other, maybe. That could be the same size, but they're different frequencies by assumption in this case. And what you have is a net function where the motion is the sum of these waves. You oscillate about the bigger one with the smaller one. So it kind of crosses here like that. Crosses this one again here where this one's, where that's zero, and then when it's zero again, it has to cross again. So it crosses here, goes above it, and then where this crosses the x-axis, it crosses it again. So some kind of sum of these things, and that's the blue one. So you have a sine wave and a sine wave, and then a sum of sine waves, and it should look like it wiggles a little. Well, this is very hard. It kind of wiggles around a little. Maybe kind of like that. I have a picture in the notes. All right, so that's what can happen, but now what happens if omega equals omega naught? If omega, which is square root k over m, is equal to omega naught, the natural frequency of the mass on the spring, square root k over m, angular frequency, is equal to omega naught, the driving angular frequency, then what happens? The particular solution changes. The homogeneous solution is the same, right? A sine square root k over m t plus p. But the particular solution cannot be of the same form. Remember when you drive it with the same frequency as the natural frequency, what you've got is the undetermined coefficients says that the homogeneous solution will be a solution, the particular solution will be a homogeneous solution unless you multiply by t. So you have to put k equals 1. So undetermined coefficients with k equals 1, you have to multiply it by t or you'll get a solution to the homogeneous problem. Is at sine, and it gets square root k over m again, p plus p0, because omega equals omega 0 in this case. And now what happens? This one is a sine wave. It just goes like this. Right? But this one is a sine wave times t. So it goes between this line here, y equals a0t, and this line here, y equals minus a0t. I'm just looking at that, and it multiplies by a number that goes between plus and minus 1. And your solution is this one plus this one, but this one goes like this, gets bigger and bigger. We call this resonance. If you drive the mass on the spring at the same frequency it wants to naturally oscillate, it's like pushing your little kid brother or sister on the swing, right? What do you always do with them? And they come back every time you push them again. You push them again, they go higher and higher and higher, right? That's what happens to the mass in the spring. It takes bigger and bigger in oscillations, theoretically getting arbitrarily large. Now your little brother or sister doesn't get arbitrarily high because there's actually friction in the swing. But if there wasn't, he or she would just go around. And same thing happens here. This would get bigger and bigger, except damping comes in and knocks it out, or the spring, the spring gets stretched too far and fails to be a Hooke's law anymore. You don't extend the spring. But that's what you get, is you get a motion that's the sum of these two, and this one starts to dominate, right? This one's just a little wiggle around it after a while. That's resonance. Let me show you a video, what can happen in that. And I'll have to do my examples on that next time. If you go to the notes, so All right. We didn't get to do the phenomenon of beats that I showed you at the beginning. We'll have to do it next time. But here's the one where it's the sum of two sine waves. If you're pushing it with this sine, if the particular solution is this sine wave and the homogeneous one is this sine wave, or vice versa, the sum of them is this dark one that just kind of wiggles back and forth around the bigger one. So that's if you're driving at a different frequency, just does that sum of sine waves. Here's what there's beats that we did before. We'll get to that. Here's resonance. This is what we've got now. The mass oscillates up and down wildly, and there is a wonderful picture in here. It's coming up in the next section. I just want to show you what resonance happened in real life. This is a beautiful video. You won't be able to get the sound here, but it shows how the Tacoma Narrows Bridge in the state of Washington, built in 1940, under a 40-mile-an-hour wind. It's not very big. We get those all the time here, right? The wind built up huge oscillations in the bridge because it oscillated the bridge at its natural frequency, and it built up bigger and bigger vibrations till the bridge fell down under a 40-mile-an-hour wind. This is actual footage, so it's amazing. Sometimes the bridge is moving like that. See, it's real time. Keep going over time, so you will stop this. So I'll give you the link to that. Since I'm slightly over, let me just send you all the homeworks and the link to this and everything. Thank you for coming in today. See you next time.